Hello everyone. Welcome back to my channel Chemical Adda. If you're new here, don't forget to hit that subscribe button and turn on the notification bell so you never miss out on our informative videos. So, in today's video, we are going to learn about different types of common equilibrium diagrams that are typically seen when working with leaching operations. But, if you haven't watched our previous videos that explain the basics of leaching, solid-liquid equilibria in leaching, single-stage leaching, and graphical representation of equilibrium, make sure to check it out first. The link is in the description box below. It'll help you understand the basics before we move into this topic. So, let us move on our today's topic. In leaching operations, different common equilibrium diagrams are used to help us to understand how solute distribution behaves at equilibrium between solid and liquid phases. So in this video, we explore three key types of equilibrium diagrams. Hence, the first type of equilibrium diagrams is solute C is infinitely soluble in solvent A. So the condition for the first type of equilibrium diagram is that solute C can dissolve in any amount in solvent A without reaching a saturation point. Then the second type of equilibrium diagrams is no adsorption of solute occurs. So the condition for the second type of equilibrium diagram is that the solid phase doesn't retain or adsorb any solute. And because of that, all of the solute will only be found in the liquid phase after the equilibrium is reached. And the third type of equilibrium diagrams is solute C has limited solubility. Hence the condition for the third type of equilibrium diagram is that solute C can dissolve in solvent only up to a certain limit. And beyond that point, any excess solute will remain undissolved. Now, let's understand this in detail, one by one. So, let's start with the first type of equilibrium diagram. Type 1, where the solute C is infinitely soluble in solvent A. A common example of this type is soybean oil being leached from soybean meal, using hexane as the solvent. Now, look at the graph. In the upper graph, the N versus X and N versus Y curves show how the N changes with solid and liquid compositions, where N is the ratio of inert solid to solution. X is the solute concentration in the solid phase, and Y is the solute concentration in the liquid phase. It helps us to understand how N varies with both solid and liquid phase solute compositions. Then we can see that, in the lower graph, the Y versus X curve is curved equilibrium line, which represents solute transfer from solid to liquid is gradual. Then, we can see that in the upper graph, the values of X and Y can range from 0 to 1. So, as we know in this case, solute C dissolves completely in solvent, without any solubility limit. Hence, the values of X and Y, representing solute concentrations in the liquid retained by the leached solid and the withdrawn leaching solution, can range from 0 to 1. Then, we can see that in the upper graph, the curve GJ lies above the X-axis, which shows that N is greater than 0. Hence we can conclude that the withdrawn leaching solution contains some solids B. And this is because either solid B is partly soluble in the solvent, or an incompletely settled liquid has been withdrawn. Then we can see that the tie lines are inclined, and they are not vertical, which implies that X is not equal to Y star. This indicates there is non-uniform distribution of a solute between the two phases occur, and which is possible due to if there is insufficient time of contact with the leaching solvent to dissolve all solute. Which means that, if the leaching solvent doesn't get enough time to fully dissolve the solute from the solid material, then equilibrium is not reached. And because of that, the solute remains partly in the solid, making the tie lines slanted instead of vertical. Then second reason may be if preferential adsorption of the solute occurs. So sometimes, the solute doesn't just dissolve in the liquid, it gets adsorbed onto the surface of the solid. This causes unequal distribution of solute, which makes the tie lines non-vertical. And the third reason may be if the solute is soluble in solid and distributes unequally between liquid and solid phases at equilibrium. Hence, if the solute is partly soluble in the solid, it will distribute itself between the solid and liquid phases at equilibrium. Which means that the solute doesn't completely leave the solid even at equilibrium, and because of that tie lines are slanted. Now, let's move on to the second type of equilibrium diagram, which represents an ideal case where no adsorption of solute occurs. So as in this case, solute C does not absorb on solid, and hence, withdrawn leaching solution and solution associated with the leached solid have the same composition. Hence we can see that, in the upper graph, the n versus x and n versus y curves show a straight line, which means n is nearly constant. From this we can conclude that, the n, that is ratio of inert solid to solution, does not change significantly with respect to solid or liquid compositions, and it remains relatively stable during the leaching process. Then we can see that, in the lower graph, the y versus x curve is a straight diagonal line. So as the equilibrium line is perfectly linear, and forming a diagonal, from the origin to the top right corner, which means that solute concentration in the solid and liquid phases is always equal at equilibrium. Then we can see that, tie lines are perfectly vertical. This is a unique characteristic of this diagram. From this we can conclude that, the composition of the withdrawn leaching solution and the solution retained by the leached solids or sludge is identical. And this results in, the XY curve in a lower figure identical to the 45-degree line, which represents an equal distribution of solute in both phases. And that's why, in this type we can consider, y star is equal to x, which implies that, a distribution coefficient, that is m is equal to y star divided by x, is equal to 1. Then horizontal line KL represents, a constant ratio of inert solid to solution in the slurry. So is line KL being horizontal, which means that the amount of solid drained or settled is constant, across all solute concentrations, and hence the solid-liquid separation is uniform at every stage. Then we can see that, the n versus x curve lies on the x-axis, which indicates that the liquid solution does not contain suspended or dissolved solid B, and solid is completely settled or separated from the liquid. So that, the solution phase is free of solid impurities, and contains only solvent A and solute C. This type of equilibrium is ideal, as it implies perfect solubility and no interaction between solute and solid. Now, let's move on to the third type of equilibrium diagram, where the solute C has limited solubility excess in the solvent, and excess solute may even crystallize out. Which means that, solute C can dissolve in solvent only up to a certain maximum concentration. And once this saturation point is reached, it is not possible for any solution to have a higher concentration of solute C. And, if additional solute is added beyond excess, it will no longer dissolve in the solvent, and will remain in the system as undissolved solid particles. So, we can see that in the upper graph, n versus y curves follow a steep curve. Hence as n versus y curves show a steep nonlinear trend, from this we can conclude that, the mass ratio n decreases sharply as the leaching operation progresses. This is due to the limited solubility of the solute, which restricts how much can dissolve in the liquid phase. Then we can see in the lower graph, the y versus x shows the diagonal curved line, which starts from the origin and rises up to a certain point xs. And beyond excess, no additional solute can be dissolved in the liquid, and the solution becomes saturated. Hence in this case excess is saturation point. Then we can see that, in the upper graph, the point M is lying to the right side of line PS. From that, we can conclude that, any mixture like represented by point M, with composition beyond saturation limit XS, will settle into a clear saturated liquid solution represented by point S in the upper graph, which contains solute C at concentration XS. And a slurry represented by point U, which consists undissolved excess solute C, whose amount depends on the initial composition of mixture M. Then point T represents the composition of the solid solute phase after excess solvent is removed, such as drainage or settling. Then we can see that tie lines converge to a common point XS. This is one unique feature of this diagram, where tie lines converge to a specific point, called XS, which represents the solubility limit of the solute. This convergence shows that, no matter the initial mixture composition, the liquid phase cannot go beyond the saturation point. Then we can see that, the tie lines which lie on the left side of point XS are vertical. So, for mixtures to the left of line PS, tie lines are vertical, which indicates, no adsorption and simple equilibrium behavior, that is the liquid associated with solid, has the same composition as bulk liquid. Hence, this model is useful for systems where the solubility of the solute is limited and excess solute crystallizes out. So that's all about different types of equilibrium diagrams in leaching operations. Let's quickly recap. So there are three main common types. Type 1, where the solute is infinitely soluble and tie lines are inclined. Type 2, the ideal case, with no adsorption, vertical tie lines and uniform distribution. Case 3, where the solute has limited solubility, and we see crystallization beyond the solubility limit. So, each of these models helps in understanding how solute behaves in real leaching systems, and that's important for designing efficient extraction processes. So, thanks for watching. If you found this video helpful, make sure to like, share, and subscribe, and hit the bell icon so you don't miss the next videos in this leaching operation series. And don't forget, the link to the previous video is in the description below. Check it out to get the full context on leaching equilibrium concepts. See you in the next video.